Hi everyone, today we're going to talk about factoring using the difference of two squares. Now remember that factoring is expanding the product that we see of the binomial, so we're going to find what multiplies into x squared minus 25 for that first one. So when we have the difference, so when we have subtraction of two squares, there's a specific type of factoring that we can do. So when we have subtraction of two perfect squares, so that means we have a number where something times itself equals that number. So for example, x squared, y squared, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, and so on. When we have the difference subtraction of two squares, we can expand the binomial into the product of two conjugates. So what that means is we're going to have something plus something times something minus something. And I'll show you why that will end up canceling out to its original form. So x squared minus 25, the square root of x squared is x because x times x is equal to x squared. 5 times 5 is equal to 25, so I have factors of x minus 5 and x plus 5. Those are conjugates because they are opposites, plus and minus. If I were to multiply these out, I'd first have x squared. On the outer terms, I'd have plus 5x. The inner terms, I'd have minus 5x, and the last terms, I would have minus 25 or negative 25. Positive 5x and negative 5x cancel each other out, so we're just left with x squared plus negative 25 or x squared minus 25. But we're asked to factor. I don't want to keep that multiplying back in there. 4x squared minus 9. Well, the square root of 4 is 2. The square root of x squared is x, and the square root of 9 is 3. So I have 2x minus 3. And 2x plus 3. If I were to multiply that back out, my first two terms, 2x times 2x is 4x squared. My outer terms, 2x times positive 3 is positive 6x. My inner terms, negative 3 times positive 2x is negative 6x. And negative 3 times positive 3, the last terms are minus 9 or negative 9. The 6x's cancel. 4x squared minus 9. So trust me on those. As long as we have a minus in the middle, the difference of squares, and we put the conjugates, those outer and inner terms will cancel. So number 3 here, 25x squared minus y squared. 5 squared is 25. X squared is x squared. X times x is x squared, and y times y is y squared. So I have 5x and y minus plus. The minus and the plus, the order doesn't matter which one comes first since multiplication is associative. So no matter where you put the parentheses, multiplication is also commutative. The order doesn't matter. So in the first row, I put all the subtraction first. In the second row, I'll put the addition first. So plus, minus, plus, minus, plus, minus. Okay, so for number 4, 36x squared, 6x times 6x is 36x squared. 1 times negative 1 is negative 1. So a lot of times we skip over 1 and don't remember that's a perfect square, but 1 times 1 times 1 times 1 times 1 is 1. So 1 is a perfect square, a perfect cube, a perfect fourth, and so on. 4 is the square root of 16. 4x times 4x is 16x squared. That subtraction separates our terms. 81y squared, the square root of that would be 9y. So I have 4x plus 9y and 4x minus 9y. For number 6, that first term of 9x squared, the square root of that would be 3x. So 3x will be my first term. And the square root of 49 is 7. So for this next one, I actually want to change this. So 25x to the 4th minus 16y squared to the 6th power. Actually, I'm not going to change it, but what I want to have, if I had 25x to the 4th plus 16y squared, then I would want to look for a greatest common factor because the difference of two perfect squares wouldn't work here because it's addition. So, but if I have subtraction, which I do, I can factor like we've been doing. So 25x to the 4th is a perfect square. 25, the square root of that is 5. The square root of x to the 4th, well, x squared times x squared is x to the 4th. So my first term will be 5x squared plus and minus. And my second term, square root of 16 is 4. Y cubed times y cubed is equal to y to the 6th power. Number 8, x to the 4th minus 81. Kind of similar to number 7 in that it's not x squared anymore, but because we have that even power, we can that's still a perfect square. So x squared minus 9 and x squared plus 9. Well, x squared minus 9 is also a perfect square, so we can factor further. X squared plus 9, we can't do anything with that because it's not the difference of two squares. It's the sum of two squares, so that stays as is. That's not going to factor nicely. But x squared minus 9, x minus 3, x plus 3, and we'll keep the x squared plus 9 because that's not the difference of two squares. For number 9, 2x squared minus 18, well, x squared is a perfect square, but 2 and 18 are not. However, if I use my factoring of a greatest common factor, if we pull out a 2, I'm left with x squared minus 9. Well, that's a perfect square, or those are perfect squares rather. So we have 2 times x minus 3 and x plus 3. So you can combine factoring rules as long as you do each of them separately, but they can be done in the same problem. So for number 10, x to the 10th power minus 4y to the 8th power. X to the 10th, since 10 is an even power, it is a perfect square. So x to the 10th is x to the 5th times x to the 5th. Square root of 4 is 2. And y to the 4th times y to the 4th is y to the 8th. Number 11, 3x squared minus 75. This is the difference of two terms, but 3 is not a perfect square and neither is 75, but they are both divisible by 3. So if I factor out my greatest common factor of 3, I'm left with x squared minus 25, and that's a perfect square. So 3x minus 5, x plus 5. And the last one here, number 12, 8 is not a perfect square, but 32 is also not, but they're both divisible by 8. So if I factor out my greatest common factor, I'm left with x squared minus 4, and that's a perfect square, so I want to factor further to x minus 2 and x plus 2. So that's an introduction to the difference of two squares. Let me know below if you want to see any other problems.